you. So for this session, we will actually change the topic, but this will be sort of a continuation on both what we have talked about earlier today, which was GPUs, and on the container session that we had yesterday. So how to use containers on HPC systems. So the topic for yesterday was perhaps more in the traditional sense of or use case for containers, where you want to encapsulate a small workflow of some kind, or your environment just to run without interfering with anything else, and possibly many different containers running on the same machine in complete isolation. But here we will try to do something a bit different, which is more in the traditional HPC way of thinking, where we really want our programs to make use of all the sophisticated hardware that we have on the cluster, and we want it to. Sorry, I need to plug in my headset before it goes out of power. Okay. Right. So, what was I saying? So we want now to fully make use of the hardware that we have on our fancy clusters, and then what we want to do is to run these calculations large scale over several nodes, and possibly using the CUDA hardware or the GPU hardware that we have. And then the question is, how can we do that with containers? Because as Abdulrahman briefly mentioned yesterday, that there are some complications here that, and actually I see that he has joined now. That is good. So we have some help from an expert, because I'm really not an expert on this. But basically, it means that the container is not as contained as you might think, because you can imagine if you want your program to run over several nodes on a cluster, it cannot be fully contained. So it will have to interact with the environment in some way or another. And also, so for the MPI part, it means that it needs information from the communication. So the InfiniBand, for instance, if you want high-speed communication between the processes. And for CUDA, it means interacting with the hardware drivers for the GPUs. And then it becomes a bit complicated, because you need to put this into the containers, as well as having the things available on the cluster. So it has to be some kind of interplay between the container and the host environment on the cluster. But again, as before, as yesterday, we will not touch upon building any containers, because this is something you really need to take into account when you want to build an MPI or a CUDA container, because then you need to put a lot of software into the container for handling all this. But here we will only use existing containers, just as before, as yesterday. Okay, so let's move into this example then. So what we want to do now for this last session is to run code called BigDFT, and we'll run it through a container using both MPI, actually MPI plus OpenMP. So it's a hybrid traditional parallelization scheme running on the CPU only, and then we'll try to use the CUDA version of the same software. And why big DFT? No real reason for this. So what it is, it's a so DFT here stands not for discrete Fourier transform. If you are in mathematics, that's what you know DFT as. But in chemistry, it means density functional theory, and this is what it is. So it is a electronic structure code for computing energies and properties of molecular systems. So more than that is not really necessary to know. So I've chosen this example basically because it is a good example that touches upon both. So within containers, so it is containerized already, and it has support both for MPI, OpenMP, and CUDA. So you can sort of test all of this using the same software. And it's also very easy to run. So within the container, it actually comes bundled with everything you need for running it. So you don't have to write any complicated input files and stuff like that to make it work. So what we'll actually demonstrate in this example is these 5 steps here. So we touched upon some of this yesterday, so how to bind a work directory from the host into the container. So this means that from within the container environment, you will have access to files that are located on the host. So that's obviously important if you want to run calculations where the input files and the output files should reside on the host side, so not just inside the container. Then we'll also touch upon how to copy files from within the container to the host. And this is something we did not do yesterday. As I said, this big DFT container comes with some pre-made input files that are located somewhere inside the container. So we need to find them, and we need to extract them and put them onto the host so that we can use them. And we'll also see how to run an interactive shell inside the container. And I don't know if Sabri, you touched upon this yesterday. I don't remember any example on that.
I accidentally did that, Stig, but I did not explain.
Okay, perhaps he's not present still. Anyway, we'll show how to do that. And then, so the main purpose here, of course, is the last 2. So how do we launch a container in this setting? And how can we make use of this MPI functionality through a container and CUDA as well? Okay, so so first of all, where can we find this big DFT container? And Sabri showed this website yesterday. So this is the NVIDIA GPU Cloud, NGC. And I saw also some discussion in HackMD here in the last break about TensorFlow being difficult to work with or compile. And it was also mentioned yesterday by Sabri that PyTorch TensorFlow could be difficult packages to work with and to compile to get working correctly. But here we have many of these tools already pre-compiled and set up so that they should work within a container environment. So this is a good place to start for many things. So what we'll do now, go into containers here. It's probably a bit small font, but and then we'll try to find. So you can see there are a lot of different things. So okay, Quantum Espresso is another chemistry code that is available from this NVIDIA cloud, and GROMACS, also a huge code that you might be interested in. And there are some development frameworks, so CUDA environments. So this was actually the topic of the example that I will not show, that I linked to in the program today, where we would use a CUDA environment from a container to build and run a CUDA application. And it was actually using this one. So it was downloading a CUDA environment from this same NGC cloud. So let's see if we can find big DFT here somewhere. Okay, a lot of different tools available. Maybe I just have to, also it's MATLAB even. Maybe I just have to search. Ah, there it is, big DFT. Okay, so first what you should pay attention to is, of course, that the system requirements is met. And this is especially for these types of containers with MPI or CUDA, because they, as I said, they require some software to be installed inside them that is compatible with the host that they want to run on. And this, of course, has implications for the portability of these containers. So they will naturally not be as portable as your regular containers that do not have any of these technologies inside. But you can see here we want, this has been, this particular container that we will use has been built for Pascal GPUs. And if we remember from the NVIDIA SMI that we showed in the last session, this is exactly what we have on Saga. And Volta is actually the one that we have. If you paid attention in the NIRD toolkit yesterday, you would see that the GPUs on NIRD are Volta, so they are V100. So these can actually run there as well, if you want. But it is not supported for the GPUs on Betsy, which are A100 for Ampere 100. So these are, it will not be supported for that. And also that the CUDA driver is newer than this one. And okay, if we just go back to the GPU node on Saga that we have, and quickly look at the output from the NVIDIA SMI. Here you see, so first of all, we have the P100, which is the Pascal card, so it's good. And the driver version is 455, so we are good there as well. And finally, that the Singularity version that we have on Saga is good. So we have version 3.7, and so it is met. Okay, so then we go to the tags. So the different containers that we can download and use. So there are actually only two here, and there are some telltale signs here for what is included inside this container. So we have the operating system. Well, first of all, the CUDA version. So we have 9 or 10. And we have an operating system which is Ubuntu and quite old, so either 16 or 18. And we have an MPI library, which is either MBA Pitch 2 or Open MPI 4. And then we have MKL math library inside. So we will use the first one here. It's the most recent, and it has the Open MPI version 4 inside. Okay, so how to download this? So this will copy the download command. And let's see, first, where are we? On Saga. So I'm still in this projects directory under my name, and we worked in the session 1 before the break, and I will now make another one for session 2. Oops. So again, here empty. An empty folder, and this is the command that I copied from this. Okay, so there a pull tag or up there, then it copies the command to download this particular container. Now you can see this is a Docker command, and this is not what we want to use. So we cannot use this on our systems, if you remember from yesterday. Oops, wrong window. So what we have instead, we need to change this to Singularity, and then the Docker goes here instead. So Docker : / and then we have the address here. So NVCR, it's NVIDIA Container Registry, and it's the big DFT container, and we want this version, which is the same as the one we have there. Okay, so I will just enter that command, and you can see here that I'm actually using a cached image here, and that is deliberate because it takes a few minutes to build this the first time. So if you do a Singularity pull on this image, it will take some time to build, but now it should be much faster since it's already cached in my home folder in Saga. Okay, here let's go back to this one and see what we need to do. Okay, so a few words on the MPI issue here. So there are basically, so since we are dealing here with both an MPI library on the host and an MPI library inside the container, and they need to interact in one way or another for these calculations to run. And this might be a bit complicated to fully understand, but you can think of it as, so there are now 3 ways that we can combine these things. So either, and as far as I know, all of these should in principle work. So maybe Abdul Rahman can correct me if I'm wrong here, but I think it should be possible to launch an MPI calculation with only using the MPI library inside the container. However, I've not been able to do that on Saga. I've tried many different things and it was not working. Then the other extreme would be to only use the MPI library on the host. And in that case, you would have to bind the host MPI into the container in some way, so that the application inside the container will use the library outside the container. Again, I have not been able to make this work on Saga for whatever reason. That could either be that our MPI libraries on Saga is built in a particular way that this is not possible, or that our Singularity is configured in a way that this is not possible, or most likely that I'm doing something wrong. So then the third option, of course, is to combine them, where you use the host MPI to launch the job, and then you pass on some handle for these MPI processes that has been spun up on the host into the container, and then the program runs inside the container using the MPI library inside the container. So this sounds like the most complicated setup, but it's actually the one that I've made work on Saga. So now I have downloaded this container. Actually, I should have renamed it something else. So if you copy this, not that string, this one, it will actually rename the file that you get down. So here it's called the same thing as the image, as the address to the image, the tag on the image. But this is actually one nice thing about Singularity images, in my opinion, compared to Docker, for instance, is that these images are simply files. So they are binary files, as you can see here, and you can rename it if you want. So I will rename this into big DFT CUDA to make it fit with the commands that I will use in the example. And you can move them around as you like. So it's just a file. So you can copy it around, and you can even SCP it to other machines and it will work there. So you don't have to use the Singularity pull command to get containers into Saga, for instance. If you have one container built locally on your machine, you can SCP it to Saga and run it, and it will work. You can also, so now I renamed this to be called Big DFT CUDA, and you can, depending on how it was made, the container, you can make it behave just like an executable. So let's see if this actually does anything. Nope, it does not. But that's because the developers have not enabled that thing. Okay, so right, so the big DFT container has not been configured in a way that you can execute it in this way, I think. Or does it? Oh yeah, actually it does. Anyway, so what I will do now is try to run it with MPI first. So no CUDA at this point. So first of all, as I said, this container comes with some input files somewhere inside the container. So we will start to have a look inside. Actually, I will switch place on these. Make it more visible for myself, at least. So if I do Singularity shell, oops, into big DFT, into the container. So this command will give me a shell prompt inside the container. So now I'm in the container environment. And if you remember from yesterday, there was some issue with the binding of the directories from the host. If you want to access files from the host inside the container, you need to bind correctly. And since I now did not do this, and we were located in the project directory, it means that now that I'm inside the container, I actually land in my root home directory. So this is the same as my home directory on Saga, because that is mounted or bound automatically. So it means that I will not have access to the directory where I entered the container in this case, but it doesn't really matter. Now I just want to take a look at the files that comes with the container. So you can see it now. We should have a big DFT command inside the container because that's the purpose of this container. Let's see if that one has a version. Okay, probably not. Not sure what. Okay, anyway, so let's go into this directory docker fehib inside the container. So docker. So first, here you can see there are a few files that comes with the container image that you can test out and use. So some examples for how to use it. And we will do this fehib example, which you can see comes both in a GPU and a no GPU version. So we'll start with the no GPU. So again, if I look at the no GPU, here are the input files that we want to run and test. But for now, these are located deep inside the container, so I need to extract them in some way. And I cannot do that easily now because I have not mounted the work directory that I want to run these from when I entered the containers. I will first exit it. And now I'm back to the project directory there. And then I will instead run this long complicated command here. So first I will do a Actually, let's just keep it simple. I will copy it into the current directory. So I will not do exactly as is written there. But here, Singularity exec, and I bind not to home big DFT test, but to the current directory. And I bind it into the container and call it work did inside the container. Then the path to the container is also not home, but it's immediately available here in my current directory. And then I run this command inside the container. So bin bash -c, this means that I run a bash command and I will interpret this string here as the command that is supposed to be run. So that's the C option. And it means recursive copy of this node GPU into the work directory that I just created inside, which is the current directory outside the container. So that might be a bit confusing, but this is the way to extract data from inside the container out to the host. So I'll just run this and see what happens. No errors. And now you can see we get a node GPU directory here on the host. So I'm still now on the host, not in the container. And if I go into that, you see the same files that we found inside the container. So that's the way to extract things from within the container. Yes, and one note here. So we have seen the ways to get things into the container by binding some directories when you enter the container. That makes files accessible inside the container if you want that. And now this is a way to copy things out from the container to the host. But the last thing, which is actually not possible, is to copy files from the host into the container, because they are read-only. So you cannot change the container, the content of the container. So it's actually not possible to copy outside files into the container. So that would be in the build step of the container instead. And that requires root access to the machine that you are running on. So we will not do that now. So to run this example, I will just copy this run script. Okay, we'll not use the same names that in the example, but okay, and then we need to discuss some of the issues here. So first of all, I ask for 2 tasks, so MPI tasks, and 10 CPUs each. So 20 CPUs in total, and they should be distributed as two processes with 10 OpenMP threads, and some memory and time. And now it's important, I need to load an MPI library on the host, and it needs to be compatible with the MPI library that comes with the container. So that makes it important to look at the, so if you remember the name of the container, or the tag on the container said OMPI 4. So it means that you should choose an OpenMPI version 4 point something. Then you are usually fine. Then in order to run this, so as I said, in the hybrid way of launching MPI containers, meaning that we launch the job MPI run on the host first. So you set up the MPI calculation on the host, and then you pass on this into the container so that the container library takes over once the process starts up. So this means that we do this MPI run on the Singularity command. So if we first don't bother about this thing. So you can see MPI run on the Singularity exec command. So that's the first thing. Then we bind the current directory, because here are all the input files, so that big DFT knows, finds the input files when you run. And then the path to the, let's see, to the container, which is not this. I will just write the full path, projects, it was in session 2. Okay, let's like that. And then inside the container, we run the big DFT commands. That is the name of the executable inside the container. So this is really the command that we run, but we launch it with MPI run outside. Now the important thing with this bind to none, I don't know if I don't have time to go into that. It relates to the things that we discussed on the second day of this workshop on how to make sure that the processes land on the hardware resources, so the cores that you want. And if you don't use this with OpenMPI, actually these 2 tasks that the MPI ranks that we spin up, they will be bound to 1 core each, which means that all the 10 OpenMP threads that are spawned by these are also bound to the same core. So this is a bit annoying that you have to specify. So this is not the most efficient way to fix this. So this will just tell it not to bind to anything, which means that it can basically jump around to all the cores that are accessible to it. So you could be more specific and bind it to specific cores, but for the sake of simplicity, we will not do that here. And Ola mentioned back then that Intel is usually good at this, so you can trust Intel's defaults typically. So if you use Intel MPI, you would probably not need to specify anything like this. But for OpenMPI, you actually have to do this if you do hybrid calculations. So MPI plus OpenMP calculations. That's a bit annoying. Okay, so let's try to run this one. Okay, we are down there, and Spatch run. Okay, again, I call the script a bit differently. Now I realize I forgot to use the reservation, and I can still do that on the, even if I'm not using using GPUs for this particular example, but now this should go straight through the queue. Oops. That's probably not correct. Let's see what Slum says. So it actually picks up the, didn't I use? This is always a good idea to do a module purge in the beginning of your script. So let's try with that one instead. First, remove the output. Run it again. So now it's running. Okay. Hopefully it should be less than a minute, but when I tested this yesterday, it actually varied a lot with the CPU time for some reason, but let's hope it's not too slow here today. So there it finished. We can have a look in the Slurm output file, and it doesn't really give that much information. It just tells that the log will be written in this file instead. And we can open that. It's a YAML file, but it's not very useful. It produces a lot of printed output, so we will not bother about this. But instead, what we'll do is just to verify that things run correctly. There are also some scripts inside the container that will take care of this. So again, we will do a shell. So I will step into the container again. And now I will bind to the current directory so that we have access to the output files that are currently in this directory. And I need to find the image. Okay. So now we are inside the container and I still have access to the output files. So then I will just run this command. This is a long, complicated string of commands. This is just taken directly from the official documentation of the big DFT container. So it's nothing that I came up with myself. So inside the container, under user local big DFT, there is a Python 2 actually script available that will just verify that the calculation was working as expected. So it runs this script and it accesses the output file from the calculation, which is log YAML, and it uses these references from inside the container to verify that things went well. So let's see if it worked. Yes. I don't know if you can see the output here. Maybe change. No. Don't have time for that. So, okay, what we can see here is that the maximum discrepancy is 10⁻⁹, so it's probably good within the tolerance. And it took 16 seconds to run, and it's report success. Okay, so that's good. So it's working. So let's exit the container again, and let's try the same thing using GPU. I need to speed up a bit here to actually be able to run this, but using the GPU is not that complicated, really. So I will first do the same thing as we did for the no GPU. So I do Singularity exec, and again, I need to, actually, I will use the old okay, so this is the command that I used before to extract the input files from inside the big DFT container. So I will do the same thing now. So I bind the current directory into the container, and we run this command to copy the files. But now we will copy the GPU files instead. So now we get a GPU folder out here, and I will go into that one. And here we have input files that runs GPU. And now how can we tell that this is a GPU rather than a CPU application? So the big DFT, this will vary between different codes. Some of them will have special executables for the GPU version. But for big DFT, the thing to look for, so this is not really important, but it's basically in the input file. So you give a keyword in the input file that tells it to run the CUDA version. But again, this is different for all codes that you might want to use. So then we'll try a script for running the GPU version here. Again, I call it run.sh. And now you can see for this, okay, first change the, it's 7, and use the reservation. So you can see I ask for just a single task. which comes with just a single CPU. But I also ask for one GPU and specify the accelerator partition of the system. So in this case, you can see that there's no need to load an MPI library because we're not using MPI in this particular example. And otherwise, this is more or less the same, and we don't have the MPI run command before. So again, let's do the full path here, projects. Session 2. So that's the path to our container. So the only difference here is really the --nv. So that could be basically the end of the container GPUs with container session is just, okay, you add this keyword to your Singularity command. So this tells Singularity that there are specifically NVIDIA GPUs available to the for the container to use. So if you don't specify this, the container will not know that there are any GPUs available. So this is basically the same as in the Slurm example that we did in the beginning. If you don't tell Slurm that you want to use GPUs, when you get into the node, the GPUs are invisible to you. So you don't see that you have these resources. And it's basically the same here. So you just have to give this option to Singularity. So NV is specific for NVIDIA. For AMD, if you have that on your system, so on Lumi soon, that would be --Rockem instead. But otherwise, it should be the same. So let's just quickly, before we end, try to run this and see if it runs any faster than the CPU version. So remember, the CPU version was using 20 CPU cores in total, because there were 2 MPI processes with 10 cores each. And this one, if we go back to the script, we only use 1 CPU core and 1 GPU. So it's always difficult to compare the performance between a CPU versions of a code and a GPU version of a code, because what exactly are you supposed to compare? So should you compare a GPU with a single CPU run, or with a CPU run that uses all the CPUs on a machine versus something that uses all the GPUs on a machine? It's a bit arbitrary. But here at least we have running only 1 GPU versus 20 CPU cores. So let's see how this performs. So now it has finished, and let's do the same thing to test if it ran correctly. So I will Singularity shell into the container, and I will do bind to the current directory. And now I will run the same complicated string, the Python script that tests the output to see if it's ran correctly. Okay, so now you see it ran for 20 seconds in this case, compared to 15, 16 seconds on a CPU, on 20 CPUs. But it still succeeded successfully, or ended successfully. So if you go back to the, if we go back here to the, when I actually made these examples some time ago, they were taking only 11, 12 seconds, both in the CUDA version and in the MPI version. So they were taking the same amount of time. And I really don't know why this has changed. So this is perhaps something we need to look into and try to figure out what happened. But okay, I think that is it for now. So we can probably move on to some Q&A.
Yeah, thank you, Stig. Is there any questions you want to ask directly? Please raise your hand. Yeah, Seaman, please go ahead.
Hi, so I have a question. Do you know how this timing is compared to native builds?
Yeah, that is. So for the GPUs, I don't have enough experience yet. But for the MPI type of containers, it depends a bit. So the MPI part, there's really not much overhead at all. So for the actual communication and for the startup time for the MPI and stuff like that should be the same. Where things might get a bit less performant is that sometimes you want these containers to be more generally built so that they will work on different machines, and then you cannot use all the fancy hardware specific optimizations, for instance. But for the MPI part by itself, it really shouldn't make a difference. And actually, some of the MPI benchmarks run faster for some reason on containers than on the bare metal.
So if I understand correctly, you can build general containers, or you could build much more tailored containers. If you build tailored containers and use them, there will be very little to no overheads.
Yes, that is my experience, at least from what I've tested. Yeah.
Just a more, let's say, detailed on that. So if you build a container that is compiled for a specific architecture, like for example, you are building something for ARM, it will not work for Intel, for example. But for modern processors, the different processor releases will make difference in the performance. So if you compile and build the code for a specific processor release and you run it on another one, it will run, but it will not give you the performance you want. So for the container, as I said, the containers, they abstract everything above the kernel, the operating system, not below. So if you want to get the best of performance, you need to have the code compiled for this specific architecture.
Yeah, thanks a lot.
Thank you. Is there any more question? So I just want to remind you to give us your valuable feedback for the day on the HackMD. And I have posted a questionnaire, post-training questionnaire for you to fill up. Please give us your feedback. So this is important for us to plan the next event. So I would encourage everyone to fill up the post-training questionnaire. The link is posted here, and you can find it in the HackMD on the top of the HackMD document as well.
One more thing, maybe, because this was passed due to the sound problem about the MPI. There are mainly two options: either to install the MPI in the container and start the MPI dispatch from the host and use completely the internal MPI, or to install MPI in the container and use the mounted MPI from the container on the host. But then you need to mount the right libraries. I can maybe share my screen in a second to show you how it looks like, if I'm allowed to.
Yes, please steal it.
Okay, maybe you can give me a permission.
You can stop sharing, Stig, so that.
Okay.
Yeah. So
yeah. So quickly, have you actually made this work on Saga?
Yes.
Because I've tried this many times, but couldn't make it work.
I'm not sure how it is on Saga actually, but I can show you something in Lumi. Let me first.
Oh, nice! A sneak peek into Lumi. That's good.
Yeah. So this is H to Lumi. So this is what you will see when you log into Lumi. And I have actually a script here. Yes. So this is a Singularity script. And here I made an impage container because this is the impage that the MPI version that we have on Lumi. We don't have OpenMPI. And here I'm using srun, which use PMI, and this is when the actual scheduler controls the MPI. It is something similar to MPI run, but it's Slurm who controls it. So it is like you are saying MPI run, and then the Singularity exec, and this is the actual binary ping pong, and this is will give the output in the internal file, and this means that I'm using the internal MPI. Now, if I want to mount the MPI from the host, so I need to do two things. I need to put all the library paths needed in this environment variable, Singularity LD library path, and bind the MPI files from the host, bind mounted in the container. Now, once I fill in those two variables, environment variables, then the next time I run Singularity, it will run having these environment variables. Now, in this case, it will execute the container with the actual MPI from the host. So here is the command. Oops, sorry. Using MPI mounted from the host. Now, if I actually run this, and this queue, my jobs is running, done. So now let's list the internal and the Singularity. So this one will be showing the actual mounted MPI one. So, oops. This is the output file for the main. Yeah, this one, Singularity output. So here is the ping pong process output. And if I get the one with the internal MPI, it is the same. So both work. But the key word here is that the MPI inside the container needs to be compatible with the MPI of the host. So don't bring like MPI 2 point something to make it work with MPI 4 point something. They need to have like the similar, for OpenMPI, they need to have the major version similar at least. Yeah. But yeah, so, of course, if you need more assistance on Lumi, we could provide more details.
Yeah. Okay, Simon, I see you have a...
I have a different question. So what I've seen through this course is that you could download this GIF images from Docker. Does it matter if you build pure Singularity images or if you just to convert them from Docker? Is there any difference, or is it?
I can answer to that. So normally Singularity images, Docker images, all of them can be converted to Singularity without problems. For different versions of Singularity, this has been an issue, but most of these issues have been resolved. So in principle, any Docker container can be converted to Singularity, except those Docker containers who are built to run only as root. Those will fail. And this is not a smart thing to do for building a Docker image. Other than this, everything should work. And if it doesn't work, this should be reported to the Singularity team. Mostly the errors will be file permission errors.
Okay, yeah. Thanks a lot. Because I mean, yeah, this is interesting for us at least, because we want to work a lot with containers. And if we can stick with one of them, it would be much easier for the kind of maintenance and development. So thanks a lot.
The short advice is this: do all the shit in Docker, build everything in Docker, and then convert to Singularity and use it on HPC with Singularity.
Yeah, thanks. So this is the message I had gotten. So thanks.
Okay, one more comment on the launching the MPI, so the different ways of launching MPI containers. So you saw you had to bind a lot of different libraries into the container to make it work with MPI. So this is probably where I messed up when I tried this myself, because I ended up in this cascade of dependencies. So once I bind something in, I need to bind something else, and then I just figured, okay, this is not the way to go. But probably it will work in the end if you just go to the bottom of it. But I guess this is one of the main things about this new container technology, the Sauros, is supposedly easier to use in this sense, if I'm understood it correctly. So it should be more intuitive how to run MPI containers, at least. But we still don't have them available on our systems. So
thank you, Stig. And